Hi everyone, I'm Rudrakshila Kavyashree from School of Digital Sciences, Digital University, Kerala. Today I'll present our work titled Numerical Transitivity and Numerical Layer Properties for Lorentz Maps with Applications to the CNV Neuron Model. The study was under the supervision of Dr. Shishushankar Muni and Professor Peter. So this study combines dynamical system theory, chaos analysis, and computational neuroscience through two numerical algorithms that detect chaos in 1D CNV neuron map. So in this study, I'll briefly walk through 7 parts. Introduction, preliminaries, Lorentz maps, then two numerical tests, their comparison, application to the CNV model, and finally main results and conclusion. Coming to the introduction, chaotic behavior is commonly in nonlinear systems like fluids, weather, and neurons. Our goal was to numerically verify chaos in one-dimensional discrete map. We focus on two tests, numerical transitivity and numerical layout, which is locally eventually onto. Both help identify whether a map is chaotic by checking how points spread over its domain. We applied these methods first to beta transformation and then to Lorentz maps, finally to a realistic neuron model called CNV model. So what is Lorentz map? So Lorentz maps were originated from the Lorentz interactor used to model weather systems. They are 1D representations that retain the essential chaotic property, sensitivity to initial condition, popularly known as the butterfly. Even a tiny change in starting value produces a vastly different trajectories. These maps are ideal for studying mixing, transitivity, and chaos in a simpler settings. So coming to the beta transformations are defined by T of x is equals to beta x plus alpha into mod 1. They stretch the interval from 0 to 1 by beta and wrap it in, creating a discontinuity that mimics chaotic folding. They are used in number systems, cryptography, data compression, but also known serve as a benchmark for chaos tests because then theoretical properties are well known. Chaos and its types. Mainly, we have three chaos types, which are Lear, entropy, and Devaney chaos. Lear chaos focus on pairs of points that repeatedly approach and separate. Coming to entropy chaos, it quantifies unpredictability through information entropy. And Devaney chaos, it combines three conditions, which are sensitivity, transitivity, and dense periodic points. In our study, we mainly test the Devaney type because our maps are discontinuous. Lorentz-like expanding and beta transformations. So we work with these three classes of maps. First, Lorentz-like. Lorentz-like maps are non-decreasing with a jump, and expanding Lorentz maps are strictly increasing and chaotic. And coming to beta transformation, it is a linear special case of expanding Lorentz map. We can also say that beta transformation is linear expanding Lorentz maps. So these serve as test beds for our algorithms. Coming to the preliminaries, an orbit is a sequence of iterates of a point. A periodic point returns after n steps. And coming to topological transitivity, it means any region of space eventually overlaps with any other. These ideas form the core of chaos definitions and motivates our numerical tests. So as we can see here, this is uh, these red regions are the regions in the first iteration, and in the next iteration, these two regions are overlapping. So in numerical transitivity, this not means like it should overlap. In it should cover every subinterval. Like if we take from 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, and 0.8 to 1. These are like, suppose these are our subintervals. So in every iteration, it should cover all these points. Then we can say that it is numerical transitivity. And if in the Leo property, like if we see this, the red region is completely covering from 0 to 1. It is covering the entire portion. So coming to numerical transitivity concept, numerical transitivity is a computational equivalent of topological transitivity. It checks if a map explores its entire domain when iterated. The algorithm creates many orbits starting from random initial points and divides the domains into pins. As I said, if an orbit hits every pin, that is evidence of a dense orbit and hence chaotic behavior. Coming to the algorithm, we totally have 5 algorithms in our paper. And in that, the algorithm 1 is used for numerical transitivity test. So algorithm goes like this. In the step 1, first we'll pick a random starting point. In the step 2, it will iterate the maps many times, ignoring the initial transients. In the step 3, it counts how many subintervals are visited. In the step 4, if all subintervals are visited in any trail, we say the map is numerically transitive. This provides a quick and efficient diagnostics of case. So here is the image of numerical transitivity which we have performed in beta transformation. So this blue region is where it is numerical transitive, and the white region is it is not the numerical transitive. It is not following the test. So here is the interpretation of transitivity results. For beta transformation, the blue points in the alpha beta plane represents transitive cases. These map these match the known theoretical region and even suggest new conjectures about unexplored zones of chaos. So the test is both accurate and insightful. So coming to this figure, this is for the white region, which is not numerical transitive. And this is for the blue region, which is numerical transit. So here we can see that here it is covering the whole part, and here it is not covering the whole part. This is the main difference. Coming to the numerical Leo, the second test, numerical Leo, is a stronger criterion. If we start from any small interval, so the iterates eventually cover the entire domain. This is implemented by 4 modules. So first is merging, interval merging, image computation, coverage test, and checking the and running these for all subintervals. The test is deterministic and more computationally intensive, but gives a rigorous picture. So as we can see, this is for the beta transformation, which we have done. It is nearly same, but we do have the difference points. So this is the comparison. So here we can see there is a difference. Like the red points are numerical Leo and not numerical transitive, and the blue points are numerical transitive and not numerical Leo. But if we look at these images, it is nearly same. Coming to the introduction of CNV neuron model, now we apply both tests to biologically inspired model, the CNV neuron model. It's a 1D reduction of a 2D discrete system describing membrane potential dynamics. So the equation of CNV model is xn plus 1 is equals to g of xn. that is equals to xn plus f of xn minus alpha minus beta into h of xn minus d. So here h of x is a Heaviside step function and f of x is different for uh, piecewise linear and non-linear cases. So here comes for the piecewise linear and non-linear versions of CNV. So here is the f of x for the piecewise linear CNV. F of x is minus m naught x if x is less than or equals to j minimum, and m1 into x minus a if j minimum is less than x less than j maximum, minus m naught into x minus 1 if j is greater than or equals to j max, where j minimum and j maximum parameters are given here. And for the nonlinear case, f of x is equals to mu x into 1 minus x into x minus a. So as we can see here, why we call it as a piecewise linear in a sense, we can see the linear lines here for the linear, piecewise linear, and for the non-linear, it is it is not a linear. So these are the tables uh, and tables of conditions which we have used in our study. So these are the conditions for piecewise linear CME and these are for non-linear CME. So here are the main conditions, which is J minimum is less than equals to B, C less than equals to J max, B less than B, D less than C, G of B greater than equals to B, G of C is less than C. These are the conditions uh, for piecewise linear. And these similarly, these are for piecewise non-linear case. Numerical transitivity in CMB, these are the results. So here red points are where it is following the numerical transitive case. This is for piecewise linear CMB. As you can see, the lines are linear. And this is for the non-linear case. And this is the numerical DU for non-linear CMB. And this is for the piecewise linear. Here, the black is where it is following the numerical transitivity, and the green is where it is not following the numerical view. Coming to the interpretation, in neuronal terms, transitivity corresponds to flexible voltage dynamics and irregular spike patterns. The chaotic regime mimics real neuronal bursting, whereas non-transitive regimes produce regular oscillations. Thus, chaos enhances the diversity of neuronal responses. So this is the case of bursting of nonlinear CME model. This is for the transitive case and this is for the non-transitive case. In the conclusion, first, numerical transitivity and numerical Leo are robust tools for detecting chaos in 1D math. The second is they yield almost identical results, making transitivity as fast substitute for Leo. Applying them to a CNN model reveals chaotic spiking behavior analogs to real neurons. Our study bridges dynamical system theory and neuroscience. Thank you for your attention.